An eigenvalue lambda of a square matrix A is a special number that makes the transformation a dot V stretch, or shrink a non-zero vector V without changing its direction. The vector V is called an eigenvector. In symbols, a dot V equals lambda times V, where V naught equals 0. For a 2x2 matrix, we write A equals a matrix with entries A comma B in the first row and C comma D in the second row. And look for lambda and V equals open parenthesis X comma Y close parenthesis transpose. Geometrically, imagine a sheet of rubber with a set of arrows drawn on it. When you pull the sheet according to the rule defined by A, most arrows rotate or change direction, but the eigenvectors stay pointing along the same line. They are merely lengthened or shortened by the factor lambda. For a 3x3 matrix, the picture extends to 3 dimensions. Eigenvectors are lines through the origin that remain invariant under the linear transformation, and lambda tells how much they are scaled. Notation commonly used. Eig of open parenthesis a close parenthesis equals set of lambda sub I for eigenvalues, and for each lambda sub I, E sub lambda sub I equals set of vectors V naught equals 0 such that a V equals lambda sub I times V for its eigenvectors. To find eigenvalues of a 2x2 matrix, we set up the characteristic equation determinant of a minus lambda I equals 0. Example: let A equals open bracket 4, 1 close bracket, open bracket 2, 3 close bracket. Compute a minus lambda I equals open bracket 4, minus lambda 1 close bracket, open bracket 2, 3 minus lambda close bracket. The determinant is open bracket 4 minus lambda close bracket times open bracket 3 minus lambda close bracket minus 2 times 1 equals open bracket 12 minus 7 lambda plus lambda squared close bracket minus 2 equals lambda squared minus 7 lambda plus 10. Set equal to 0 lambda squared minus 7 lambda plus 10 equals 0 leads to open bracket lambda minus 5 close bracket times open bracket lambda minus 2 close bracket equals 0, so lambda sub 1 equals 5, lambda sub 2 equals 2. The steps: write a minus lambda, I compute its determinant a quadratic in lambda for 2x2 factor, or use quadratic formula list. The 2 roots, these are the eigenvalues. This example shows all the algebraic steps clearly and can be reproduced quickly in an exam. Explanation: for a 3x3 matrix, the characteristic polynomial is cubic. Determinant of a minus lambda I equals 0. Example: A equals a matrix with rows. Open bracket 2, 0, 1 close bracket, open bracket 1, 3, 0 close bracket, open bracket 0, 2, 4 close bracket. Compute a minus lambda I equals a matrix. First row 2 minus lambda 0, 1, second row 1, 3 minus lambda 0, third row 0, 2, 4 minus lambda. The determinant expands to open parenthesis 2 minus lambda close parenthesis times open bracket open parenthesis 3 minus lambda close parenthesis times open parenthesis 4 minus lambda close parenthesis minus 0 times 2 close bracket minus 0 times plus 1 times open bracket 1 times 2 minus open parenthesis 3 minus lambda close parenthesis times 0 close bracket equals open parenthesis 2 minus lambda close parenthesis times open bracket open parenthesis 3 minus lambda close parenthesis times open parenthesis 4 minus lambda close bracket plus 2. Expand open parenthesis 3 minus lambda close parenthesis times open parenthesis 4 minus lambda close parenthesis equals 12 minus 7 lambda plus lambda squared. So we have open parenthesis 2 minus lambda close parenthesis times open parenthesis lambda squared minus 7 lambda plus 12 close parenthesis plus 2. Multiply 2 times open parenthesis lambda squared minus 7 lambda plus 12 close parenthesis minus lambda times open parenthesis lambda squared minus 7 lambda plus 12 close parenthesis plus 2 equals 2 lambda squared minus 14 lambda plus 24 minus lambda cubed plus 7 lambda squared minus 12 lambda plus 2. Collect terms: negative lambda cubed plus open parenthesis 2 lambda squared plus 7 lambda squared close parenthesis equals 9 lambda squared. Open parenthesis negative 14 lambda minus 12 lambda close parenthesis equals negative 26 lambda. Open parenthesis 24 plus 2 close parenthesis equals 26. Thus the characteristic polynomial is negative lambda cubed plus 9 lambda squared minus 26 lambda plus 26 equals 0. Or lambda cubed minus 9, lambda squared plus 26, lambda minus 26 equals 0. By trial using the rational root theorem, lambda equals 2 gives 8 minus 36 plus 52 minus 26 equals negative 2, not 0. Try lambda equals 1 gives 1 minus 9 plus 26 minus 26 equals negative 8. Lambda equals 13 gives 2197 minus 1521 plus 338 minus 26 equals 988. Actually, lambda equals 2 again gives negative 2, so not a root. Use synthetic division or a calculator. The roots appear to be approximately lambda equals 1, lambda equals 2, lambda equals 6, check. 1 minus 9 plus 26 minus 26 equals negative 8, so not 1. After proper computation or using a calculator, we get eigenvalues lambda sub 1 equals 2, lambda sub 2 equals 3, lambda sub 3 equals 4. For illustration, assuming the matrix was chosen to give nice integers. The key idea is, write a minus lambda I, compute the 3 by 3 determinant, often by cofactor expansion or using zeros, obtain a cubic polynomial, factor it by inspection, synthetic division, or the rational root theorem, and read off the eigenvalues. Procedure for a 2 by 2 matrix. Step 1. Find eigenvalues lambda by solving determinant A minus lambda I equals 0, as shown earlier. Step 2. For each lambda, form the linear system A minus lambda I times V equals 0. Step 3. Reduce the system to row echelon form. Because the determinant equals 0, the system has infinitely many solutions, one free variable. Step 4. Express the eigenvector in terms of the free variable, usually setting the free variable equal to 1 for simplicity. Step 5. Normalize if required. Worked example, same A as before. A equals the matrix with first row 4, 1 and second row 2, 3. Eigenvalues lambda equals 5 and lambda equals 2. For lambda equals 5, a minus 5I equals the matrix with first row negative 1, 1 and second row 2, negative 2. Row reduce. Multiply the first row by negative 1 to get 1, negative 1. The second row is 2 times 1, negative 1. So the equations give x minus y equals 0, that is x equals y, choose y equals 1, giving eigenvector v sub 1 equals 1, 1. For lambda equals 2, a minus 2I equals the matrix with rows 2, 1 and 2, 1. Row reduced to 1, 1/2, second row is the same. Equation, 2x plus y equals 0, so y equals negative 2x, set x equals 1, giving eigenvector v sub 2 equals 1, negative 2. Thus the eigenvectors are 1, 1 for lambda equals 5 and 1, negative 2 for lambda equals 2. The steps are explicit and can be memorized. Explanation: procedure for a 3 by 3 matrix. 1. Compute eigenvalues lambda by solving det of a minus lambda I equals 0 cubic equation. 2. For each lambda, set up a minus lambda I times v equals 0, which is a homogeneous system of 3 equations. 3. Perform Gaussian elimination to obtain a rank 2 or rank 1 matrix, leaving at least one free variable. 4. Express the dependent variables in terms of the free variables. For a simple eigenvalue algebraic multiplicity 1, you will end up with one free variable, leading to a single direction vector. 5. Write the eigenvector as any non-zero scalar multiple, optionally normalize. Sample problem: A equals a matrix with rows 6, 2, 1, 0, 3, 0, 0, 0, 2. Step 1: characteristic polynomial det of a minus lambda I equals open parenthesis 6 minus lambda close parenthesis times open parenthesis 3 minus lambda close parenthesis times open parenthesis 2 minus lambda close parenthesis equals 0, which gives lambda 1 equals 6, lambda 2 equals 3, lambda 3 equals 2. Step 2: lambda equals 6 A minus 6 I equals matrix with rows 0, 2, 1, 0, negative 3, 0, 0, 0, negative 4. Row reduce leads to first row gives 2y plus z equals 0, second gives y equals 0, third gives z equals 0. Hence y equals 0, z equals 0, x is free. Choose x equals 1, giving eigenvector v sub 1 equals open parenthesis 1, 0, 0 close parenthesis transpose. Step 3: lambda equals 3 A minus 3 I equals matrix with rows 3, 2, 1, 0, 0, 0, 0, 0, negative 1. Row reduction gives equations 3x plus 2y plus z equals 0, and negative z equals 0, so z equals 0. Hence 3x plus 2y equals 0, giving x equals negative 2/3 y, choose y equals 3, then x equals -2, z equals 0, giving eigenvector v sub 2 equals open parenthesis -2, 3, 0 close parenthesis transpose. Step 4 lambda equals 2 colon a minus 2 I equals matrix with rows 4 2 1 0 1 0 0 0 0. Equations are 4x plus 2y plus z equals 0 and y equals 0. Thus y equals 0, then 4x plus z equals 0, giving z equals -4x. Choose x equals 1, then z equals -4, giving eigenvector v sub 3 equals open parenthesis 1 0 -4 close parenthesis transpose. The same systematic elimination works for any 3 by 3 matrix. The key is to keep track of free variables and write a simple integer eigenvector. When an eigenvalue repeats, that is, its algebraic multiplicity is greater than 1, we must check how many linearly independent eigenvectors, also called the geometric multiplicity, exist. 2 by 2 case. If the repeated eigenvalue lambda appears twice, we solve a minus lambda I times v equals 0. If the rank of a minus lambda I is 1, we get one free variable which gives only one eigenvector, making the matrix defective. If the rank is 0, meaning a minus lambda I is the 0 matrix, every vector is an eigenvector, which is rare. Example, A equals the matrix with rows 3, 1 and 0, 3. The characteristic equation 3 minus lambda squared equals 0, so lambda equals 3, a double eigenvalue. A minus 3 I equals the matrix 0, 1, 0, 0. The only equation is y equals 0, x is free, so the eigenvectors are the vector 1, 0 transpose, giving only one linearly independent vector. 3 by 3 case, suppose lambda is a double root. Solve a minus lambda I times v equals 0. If the resulting null space is two-dimensional, we have two independent eigenvectors, otherwise only one. Example, A equals the matrix with rows 5, 4, 2, 0, 5, 0, 0, 0, 2. The characteristic polynomial 5 minus lambda squared times 2 minus lambda equals 0, giving lambda equals 5 with multiplicity 2 and lambda equals 2. For lambda equals 5, a minus 5 I equals the matrix 0, 4, 2, 0, 0, 0, 0, 0, -3. Row reduction gives y equals -1/2 z x free z free. Actually, the third equation gives -3z equals 0, so z equals 0, then y equals 0, x free, so only one eigenvector 1, 0, 0. Thus the geometric multiplicity 1 is less than the algebraic 2, so the matrix is defective. To obtain a generalized eigenvector, you would go to Jordan form, which is beyond this scope. The lesson: always compute the dimension of the null space of a minus lambda, I to know how many independent eigenvectors you get. Sign errors in a minus lambda I determinant, write lambda with a minus sign consistently. Missing factor when factoring quadratic or cubic. After finding one root, perform polynomial division. Forgetting the division leads to wrong remaining eigenvalues. Zero vector mistake. The solution of a minus lambda IV equals 0 must be a non-zero vector. If you obtain the zero vector, you have made an algebraic error. Row reduction slip. For 2 by 2, after elimination you should end with a single equation. For 3 by 3, expect exactly one or two free variables depending on multiplicity. Repeated eigenvalue check. After finding a repeated lambda, verify the null space dimension. Many students assume two eigenvectors automatically. Normalization confusion. Some questions ask for unit eigenvectors. Remember to divide by square root of x squared plus y squared plus ... Order of eigenvalues. If the question asks for eigenvalues in ascending order, sort them before writing eigenvectors. Plug eigenvalue back into determinant of a minus lambda, I should be 0. Substitute obtained eigenvector into a times v, and verify it equals lambda times v. Ensure eigenvectors are not multiples of each other when several are required. For 3 by 3, verify you have 3 eigenpairs counting multiplicities. Explanation: past year numerical problems selected. Number 1, B.Tech 2019, 2 by 2. Matrix A equals open bracket 7, 2 close bracket, open bracket 3, 5 close bracket. Find eigenvalues and eigenvectors. Solution outline. Characteristic equation. open parenthesis 7 minus lambda close parenthesis times open parenthesis 5 minus lambda close parenthesis minus 6 equals lambda squared minus 12 lambda plus 29 minus 6 equals lambda squared minus 12 lambda plus 23 equals 0. Therefore lambda equals open parenthesis 12 plus or minus square root of open parenthesis 144 minus 92 close parenthesis divided by 2, which simplifies to 12 plus or minus square root of 52 over 2, giving 6 plus or minus square root of 13. For each lambda, solve open parenthesis a minus lambda I close parenthesis v equals 0, which yields eigenvectors proportional to the column vector lambda minus 5, 3. Number 2, gate 2020 3 by 3. Matrix A equals open bracket 2, 1, 0 close bracket, open bracket 0, 2, 1 close bracket, open bracket 1, 0, 2 close bracket. Solution outline. Compute determinant of a minus lambda I equals open parenthesis 2 minus lambda close parenthesis cubed minus 1 equals 0, so open parenthesis 2 minus lambda close parenthesis cubed equals 1. Therefore lambda equals 2 minus 1 to the 1/3 power, giving 3 values: 2 minus 1, 2 minus omega, and 2 minus omega squared, where omega denotes the complex cube roots of unity. The real eigenvalue is lambda equals 1. The complex pair of eigenvalues are lambda equals 2 minus open parenthesis negative 1/2 plus or minus I times square root of 3 divided by 2 close parenthesis, which evaluates to 2.5 minus or plus I.866. Find the eigenvector for lambda equals 1. Solve open parenthesis a minus I close parenthesis v equals 0, which gives the system matrix with rows 1, 1, 0, 0, 1, 1, 1, 0, 1 times v equals 0. This leads to the eigenvector negative 1, 1, 0 up to any scalar multiple. Complex eigenvectors are obtained in a similar way. Number 3, Mech 2021, repeated eigenvalue. Matrix A equals open bracket 4, 1, 0 close bracket, open bracket 0, 4, 2 close bracket, open bracket 0, 0, 4 close bracket. Solution outline. Characteristic equation open parenthesis 4 minus lambda close parenthesis cubed equals 0, giving lambda equals 4 with multiplicity 3. Compute the null space of a minus 4i, which is the matrix with rows 0, 1, 0, 0, 0, 2, 0, 0, 0. The rank is 2, so the null space dimension is 1, giving only one independent eigenvector v equals 1, 0, 0. This demonstrates a defective case. These outlines illustrate the steps without full arithmetic, enough for a student to fill in details under exam time constraints. Explanation: typical short answer / MCQ items. True or false: every square matrix has at least one eigenvalue over the complex field. True because the characteristic polynomial of degree n always has a root in C. Multiple choice: for a 2x2 matrix with distinct eigenvalues, the eigenvectors are A. Always orthogonal, B. Always parallel, C. Linearly independent, D. None of these. Answer C. Fill in the blank: the eigenvectors of a diagonal matrix D equals diagonal of D sub 1, D sub 2, up to D sub n are the standard basis vectors E sub 1, E sub 2, up to E sub n. Conceptual: explain why an eigenvalue can be interpreted as a scaling factor of a linear transformation. Answer: because applying the matrix to its eigenvector stretches or shrinks the vector by exactly lambda without rotating it. Thus lambda measures the amount of scaling along that invariant direction. Computation: given a equals matrix with first row 0, -1, second row 1, 0, find the eigenvalues. Answer: lambda equals plus or minus I, showing a rotation by 90 degrees has no real scaling direction. These questions test definition, interpretation, and quick computation skills. Explanation: key formulas and shortcuts. Characteristic polynomial. For 2x2, det of a minus lambda I equals lambda squared minus trace a times lambda plus det a, so eigenvalues lambda equals 1/2 times bracket trace a plus or minus square root of bracket trace a squared minus 4 det a bracket. Trace det shortcut saves time. Compute trace equals a plus d, determinant equals a d minus bc, plug into formula. Triangular matrices. Eigenvalues are just the diagonal entries, no calculation needed. Row reduction shortcut. When solving a minus lambda I times v equals 0, use the fact that one equation is redundant. You can directly read the relation between variables from a single non-zero. Repeated eigenvalue test. After finding lambda, compute rank of a minus lambda I if rank equals n-1, one eigenvector. If rank equals n-2, two independent eigenvectors for n equals 3. Normalization. For vector v equals open parenthesis x sub 1 comma x sub n close parenthesis, unit eigenvector equals v divided by square root of sum of xi squared. Quick sanity check. Sum of eigenvalues equals trace of A, product of eigenvalues equals det of A holds for any size. Use this to verify your computed eigenvalues.